Hello, everyone, and welcome to today's webinar, XUV Spectroscopy Fundamentals, Advantages and Developments for Probing Surface and Interfacial Charge Carrier Dynamics. I am Marie Stone of LabRoots, and I'll be your moderator. Today's educational web seminar is presented by LabRoots and brought to you by Andor. To learn more, visit andor.oxinst.com. We encourage you to participate today by submitting any questions you may have during the presentation. To do so, simply type them into the Ask a Question box and click Send. We'll answer as many questions as we have time for at the end of the presentation. You may also submit any technical issues here as well if you have trouble seeing or hearing the presentation. This webinar is educational and thus offers free continuing education credits. Please click on the Continuing Education window at the bottom of your screen to obtain your credits. I'd like to now welcome our speaker, Emily Hruska, PhD candidate at Ohio State University. Emily, you may now begin your presentation.
Hi everyone, my name is Emily Hruska. I'm a student in Dr. Robert Baker's group at Ohio State University. I'm really excited to introduce everybody at Andor today to some more background of XUV spectroscopy fundamentals. Specifically, I'll highlight the advantages and developments of the method that have been critical for my graduate research and in general for better probing surface and interfacial dynamics that's so critical for chemistry today. So a little bit about my group. I'm actually a fourth-year PhD student, not a faculty member, so hopefully my understanding is enough to kind of whet your palate about XUV spectroscopy, but I am a graduate student at Ohio State University, which, if you're unfamiliar, is in Columbus, Ohio. We are happy to host visitors from a lot of the vendors we work with, so if you're ever in the Columbus area and you want to see our super cool basement laser lab, feel free to reach out to me. And you might also find yourself at our pretty famous football stadium, which is shaped like a horseshoe for reasons I do not understand. And more importantly, we have the best damn band in the land. And here's a photo of our marching band spelling out the script Ohio, which they do multiple times at every football game if you ever want to see that happen as well. But scoping out to the greater OSU campus, here you can also see our pretty picturesque oval. The chemistry department is somewhere in the middle, far away from all of these beautiful things, and that is where we spend most of our time, in the basement, in the dark, in the cold, doing some XUV spectroscopy experiments. And just to give a little bit more background about my group, Dr. Robert Baker is the PI of the group. Our website is listed here as well as his email, which I'll show again later. He is happy to answer questions or talk about any of the applications that you might see that maybe I can't answer questions about. And then also a few pictures of my group. I realize now that I'm not on video, but I'm kind of in the center of this picture, so that's easy to find. And these are people that have worked on some of the applications I'll show later, so I wanted to make sure that they're highlighted at the beginning of the talk as well, just to give some due credit for a lot of the hard work that goes on in our lab. So I also wanted to mention that there's been a recent paper that goes into much more detail on the work I'll describe today, published by my PI and a former grad student who's now a postdoc at Princeton. I'll reference it throughout here because many great examples and some of the more detailed mathematical descriptions of XUV science can be found there. But in general, the message today is to understand how extreme ultraviolet pump probe spectroscopy can provide element, oxidation state, surface, and spin state specific charge carrier dynamics with a femtosecond ultrafast time resolution. The learning objectives that I shared before the webinar are also going to kind of outline the talk today. So I want to first focus on identifying advantages and challenges of the theory behind XUV spectroscopy and why it's taken so long to develop. Second, I would like to really focus on some of the novel physical capabilities of tabletop lab XUV instrumentation. So as opposed to things at synchrotrons or X-ray free electron lasers, what really happens in a lab-based XUV spectrometer. And lastly, I'll highlight some early examples of successful studies that have been completed in the XUV field. These are going to directly correlate with some of the physical attributes of the method. And I'll just use those to kind of back up my justification of, what is element specificity, what is spin state specificity, those kinds of things, and how these attributes are really helpful for interfacial studies. And then lastly, I would like to talk about sort of the future direction of the field that's happening both in the Baker group but outside of our group as well. So first, I would just like to make sure we're all on the same understanding about what is XUV. Before I joined my research group at Ohio State, I had never heard of this term before. So XUV or EUV is extreme ultraviolet. So in the grand scheme of the electromagnetic spectrum, this is somewhere between UV and X-rays, so that kind of helps the name make a little bit more sense. But specifically, we primarily are talking about approximately 10 to 124 EV, or if you think in nanometers, 124 to 10 nanometers, which is right in the window of easy conversion. But this is sort of our window of experimentation that I will highlight. What do these transitions mean, but also what does this specific energy region provide us with in terms of experimentation? So this XUV level, excitation energy between 10 to 124 EV, this is quite different from what most spectroscopic methods have used for a long time now. So UV, visible, near IR, these all have much lower energy, excitation energies, and that means that their window to probe is limited to sort of the most valence density of states. And when you're probing this valence to conduction band type of region, you're really probing an average of sort of a distribution of states. So we think of in solid materials, the valence states are kind of a band of states rather than discrete orbitals at this point. And so when you probe an excitation between these states, you get many overlapping features, you get features that are broadened or shifted because of bonding at specific atoms, and this causes a lot of just unclear assignments of peaks and spectra that have sort of indiscriminate fittings to them. Oftentimes we see, one really large peak with several Gaussians, and you have to try to discern which excitation you're looking at in each of the minor Gaussians. And this can be pretty complicated, although it's been around for a while. So many groups are finding ways to get around this complicated assignment and still doing really interesting and expertise projects and research with this type of method. But the good thing about XUV spectroscopy is we're actually probing a core state into our valence states. So our excitation can utilize this much higher energy and promote an electron from this core to valence state. So because these core levels don't participate in bonding, they're not going to be broadened and shifted when we look at the end game spectrum. So this core hole energy can actually act as an element specific tag. We'll look at something like a metal M edge or an oxygen L edge, which would be like our 3p or our 2s states in these specific cases, and we'll excite into our most valence state, so maybe a metal 3d state or an oxygen 2p state. So these energies, again, will be essentially an element-specific tag. And when we look at the specific excitation energy for this XUV window, we actually have many orbital edges that we can probe across the periodic table. So here I'm highlighting the first 22, and we can basically see that within this window, we have many, many bands that we might be able to probe. So these low atomic number elements, these are a little bit more challenging because we don't have many solid state samples, which I'll discuss later why solid state is so easy and gas phase or liquid phase might be harder. But we in the Baker group mainly look at things like transition metal oxides. So if I just scan over to the next slide here, you can see that a lot of the interesting metals that are at the forefront of material science today have several transitions that are within this probe window. So we see that nickel has some M edge character, which is our 3p shell, right sort of smack in the middle of our window. Manganese, iron, cobalt, copper, these are all samples that have been studied in our group, as well as many of the sort of, forefront of XUV spectroscopists today who are still developing this type of method. But these are sort of the model systems that we look at, and we can examine, much higher atomic order metallic systems as well. But in general, XUV, people think, oh, this kind of limits you because the excitation energy is so small, you probably are limited to what you can study. But in actuality, every every element that's sort of interesting in chemistry today has some orbital that lies within this energy, and we can probe these transitions. And this just will allow us to understand what's happening at the valence shell. So we're still going to be analyzing electron and hole motion throughout the valence and conduction bands, but we'll just be probing that with an element-specific tag that's due to that core level excitation. So taking a step back, so that's, sort of what is XUV, but we want to also understand where is XUV science at today. And so I've just put together this rough timeline of sort of the history of XUV science to get a better grasp on why the developments are where they are today. So XUV really is tied to the development of X-ray science, which is, nominally very closely tied together because the energy windows are so close, and this super high energy but sort of invisible light is, much more challenging to understand than something like visible light or UV light, where you can kind of, understand certain properties just with the naked eye. And this led to a much earlier investigation, whereas X-ray and XUV science is just in development, still in today. But in the late 1800s, we have the discovery of X-rays, which led to the use of X-rays for science and chemistry in the early 1900s, where we started to understand crystal diffraction patterns, and we started to really understand what X-ray spectroscopy could be. So we can understand elemental shifts, we can understand chemical shifts, and this all started in the early development in the early to mid 1900s. In 1930, Lawrence and Livingston built the first cyclotron at Berkeley, and this is, directly tied to the lab that's still there today. But cyclotrons had a slightly different setup than synchrotrons, where cyclotrons had these fixed magnetic fields, and the bending of these charged particles was essentially proportional to the momentum. So the cyclotrons were limited to fairly low energies. And after that, the expansion of these facilities became unaffordably large. So in 1947, GE sponsored the building and the investigation of the first artificial synchrotron light, which was still using visible light, but this was really in a key development in the concept of accelerating particles with higher energies. And this is basically the first synchrotron as we know it today. In 1956, we had the first X-ray synchrotron study, which happened at Cornell. And this, again, was really critical to the development of X-rays as we started to have these large-scale facilities where users could come and perform X-ray studies that couldn't be done in their labs. So it was really essential to have facilities across the nation and really in other countries across the world as well, so that experimenters could start to figure out what X-ray spectroscopy could do for them. In the 70s, we had the first fourth-gen light source, which was a free electron laser that was built at Stanford. So this opened the window to coherent light sources. And this is also critical for many XUV experiments. We need coherent light sources, which is why X-ray free electron lasers are so important. But then we found in the late 80s and then through the 90s, the development of high harmonic generation in gases. So this is a process I'll describe in a little bit, but this is how we can produce soft X-rays in the low hundreds of EVs to even less than 100 EV. And this is how the development from McPherson and then Corkum and Schaefer later in the XUV window of high harmonic generation really enables what my group does today in our laser lab. And then from the 90s through today, we're still developing lab-based and facility-based XUV techniques and practices. There are still many directions that the field can go that we haven't quite figured out yet. So the development is going to be really something that happens throughout our lifetimes, and it's quite exciting to see how this path comes about. So the benefits of XUV spectroscopy, I'll get into a little bit. Many of these relate to X-ray spectroscopy in general, not just extreme ultraviolet, but X-ray as well. And I'll highlight the XUV specific ones in a little bit. The first that I'll talk about is element specificity. So here I'm showing from my own group's research spectrum where we can see the energy windows from 35 to 80 eV. So this is XUV, but the same principle applies to X-ray spectroscopy in general. We're looking at the M to 3 edge absorption. So this is 3P to 3D transitions. And what we can see here is that the M edge transition energy is increasing as the atomic number of the metal increases. So we're going from titanium to copper here, and we can see that the peaks are shifting to a much higher energy as we go. So the effective nuclear charge is increasing from left to right on the periodic table, and this directly causes this shift of excitation energy. So what we're saying is that we're actually retaining the element-specific signature of X-ray spectroscopy, and this is essentially due to the core to valence principle of how X-ray and XUV spectroscopy work. But in practice, this is quite useful because in these cases, we have all single metal oxide structures, so titanium dioxide or hematite, which is just iron and oxygen. But in principle and in practice, actually, right now, we can construct samples that are maybe more interesting that have multiple metal centers in one sample. And for instance, if we have something that involves titanium and copper, the signatures for these metal centers are quite separable, so we can directly probe one sample and understand what's happening at the titanium sites versus what's happening at the copper sites. This has been done in our group as well as in others. We've studied heterostructures that involve nickel oxide, hematite, titanium dioxide, silicon. There's many structures that are possible that we can sort of build that maybe have better applications for photocatalytic practices. But this is the first benefit that we see for XUV spectroscopy. The second benefit that we'll see is spin state sensitivity. So here is a figure from a paper by the Zhang group, and we see that again, M23 edge absorption, these are both iron complexes, but one has a quintet spin and the other has a singlet. And what we can see is that in this case where they measure the bulk thin films of molecular complexes, they can display that the shape and position are both sensitive to the iron spin state. So the ligand field is the same and the oxidation state is the same for the metals, but the spin state is actually directly shifting this primary peak by a couple of eV, and the shape is dramatically changed, as you can see visibly. So spin state sensitivity is going to be critical for understanding how electron spin is affecting something like magnetic properties, or even catalytic processes can involve a spin crossover or spin flip. So again, this is an XUV specific benefit that is not well seen in UV vis spectroscopy, for example, where the spin state is sort of buried within much more information that you can extract from the valence states themselves. So maybe I kind of gave this away in the last slide, but here we also see that the oxidation state can affect our signal. So in this case, we have, again, from the same paper where they're highlighting XUV spectroscopy, we see that the cobalt spin oxidation state is changing from +2 to +3 between these samples. Now, the spin state is also changing here, so it's a little bit complicated. The paper has a much more grand figure where they kind of extract how all of these are related, but you'll just have to trust me when I say that the reduction of the cobalt metal from a +3 to a +2 state is causing this redshift of the cobalt main peak from about 64 eV to about 61 eV. So we see this many times in excited states where a reduction or an oxidation of a metal center will actually cause a redshift or a blue shift of your main feature. And this has helped with many assignments in my group. This is sort of like our very first question when we're doing an experiment is, if you cite an electron into a metal center, now you've reduced that, do we see a redshift as we expect? And this is sort of the basics of assigning X-ray excited state dynamics. Okay, and then the fourth benefit that I'll highlight here for XUV spectroscopy is you can also extract information about the coordination geometry of your metal center. So here's the same. Structures with the cobalt metal centers, where we have the 2+ oxidation state, different spin states, but we also have different coordinations around the metal centers. And what we find is that the shape again is being adjusted based on the coordination. So you might have more or less intensity at a certain feature or entirely new peaks, and this is all due to the bonding structure of your valence shell. So as I mentioned before, the core levels aren't participating in bonding, so they won't be shifted. However, if we compare two different states of a similar sample that have different valence bonding, what we would find is that the excitation from a core level into that valence state will be adjusted based on how the external orbitals are participating in bonding, how they might be hybridized, how they might be, sort of minimized in energy in terms of stabilization or destabilization because of the external ligand field. So this is all extracted with XUV spectroscopy as well. And as I mentioned before, these four qualities are all general phenomena that are true for core level spectroscopy in general. So this ranges from XUV to soft and hard X-ray regimes as well. However, the ability to measure core whole spectra using a tabletop instrument with ultra-fast time resolution is what's going to make XUV spectroscopy suitable for studying surfaces in a lab rather than a facility. So here is just a highlight of some of the facility options that are available, and I'll just briefly describe because probably many people at Andor are already familiar with synchrotrons and X-ray free electron lasers, but these large-scale facilities, which were developed again in the mid to late 1900s, are really great workhorses for the field of XUV and X-ray science. They can, really enable many people to travel and perform experiments at these large-scale facilities. And because of funding and just general accessibility in terms of, experimentation on site, they really enable a range of different research ideas that are great and very beneficial for the field. With that being said, traveling to a synchrotron, writing a proposal, getting the beam time that you need can be quite expensive, both in cost and in time. And, there aren't very many of these light sources, in the grand scheme of things across the US or the world even. And the ones that are available, sometimes you can't do the ideal experiment. They have lower time resolution. So at synchrotrons, we can either do picosecond time resolution, or we can start to stretch into the femtosecond regime, but we have to take a hit on the flux that we get. So, it's kind of a trade-off experimentally. With X-ray for electron lasers, we started to get into femtosecond pulses with coherent X-ray light. So this is great, but again, you're going to have to travel, get the beam time. You have a week to do your experiments, and if they don't work, you have to come back in 6 months. So the benefit of having a lab option is, I can just go to the basement and, walk down the hall and do my experiments all night if I want to, and, probably I don't want to, but I do it anyway because I can get the data that I need right there at my leisure. So while these large-scale facilities are the workhorse for X-ray and XUV science, these experimental limitations and the accessibility constraints have led to this push for the development of tabletop instruments that we can all start to develop in our own labs. So this is sort of the grand scheme of our instrumentation, which doesn't actually look that complicated when you look at it in the scheme. We do have some, some boxes on the side which are generating our fundamental beam. So we have a titanium sapphire regenerative amplifier system. This is going to generate an 800 nanometer wavelength beam with 35 femtosecond pulse duration at a kilohertz repetition rate. We have a total output of about 6 millijoules pulse energy. So this is all going to happen kind of off the screen here. I didn't include because everything on the screen here is actually home built and a little bit more interesting, and actually what's the requirement for XUV spectroscopy. So we separate our fundamental beam into two path lengths. First, I'll highlight the pump path length because that's a little bit more probably familiar. So we take our 800 nanometer beam. Using a BBO crystal, we can convert this to 400 nanometer or 267 nanometer. We also have an OPA, but we generally just use 400 or 267 wavelength light. This pump beam goes through this retroreflector mirror, which generates our time delay when we want to control transient spectra with this pump probe method. So we'll move this mirror on a stage in order to set, increase or decrease the path length to create the time delay. And then this pump beam basically just enters the chamber and interacts with the sample. So more interesting is the XUV path, which is the purpose of the webinar. So the XUV beam has very high attenuation in air, or really in most materials. So we do all of this under vacuum. So the 800 nanometer beam enters the vacuum chamber here, the first chamber, which is our XUV generation chamber. So this is where higher harmonic generation takes place. I'll talk about that in a moment. Once we get through this chamber, which has a gas cell, we're going to actually filter out the 800 nanometer beam. So through this tube is just the XUV beam propagating. The XUV beam reflects off of a toroidal mirror, which is at a grazing angle to minimize the loss of XUV absorption in the gold-coated mirror. And then from there, we just, again, go through some filters and then interact with the sample. So in our case, you'll notice that the sample is kind of in the plane of the XUV propagation. So we are actually reflecting off of the sample and then onto a grating and finally collecting on the CCD. But there's also options for transmission through a sample, or absorption, I guess you could call it. I'll talk about these in a little bit. This is a pretty critical choice for what happens with your XUV spectrum at the end of the day. But yeah, this is a critical choice. But first, I'll highlight what high harmonic generation is taking place. So this is a highly nonlinear strong field process that operates in the non-perturbative regime. So it's a pretty physical process that's studied by many people in physics, mostly. So in chemistry, we utilize it gladly, but we don't study it in depth. But I'll just give an overall description of how this enables the production of XUV and soft X-ray pulses with femtosecond to attosecond pulse durations. So essentially, we have the 800 nanometer beam, and we also have a 400 nanometer beam that focus at the end of this gas cell. They overlap in time and in space, and here is where the XUV production will occur. So in step one here, we have the tunnel ionization of an electron from its gas parent atom potential into the continuum. So this happens due to the distortion of the atomic binding potential in this high intensity electric field. So at the minimum, we would distort it one way, and that electron in the gas atom can tunnel ionize out of its potential. Then as the laser field flips, we're going to actually accelerate this ejected electron back towards its parent ion as the electric field kind of reverses sign. So we distort it the opposite way, and now that electron is going to actually be accelerated back. And in step 3, XUV beam is created as the electron recombines with its parent ion. It's going to release this this photon, which is going to be in the XUV window, depending on the energy of every process that's happening here. So the maximum XUV photon is going to have energy proportional to the electron ponderomotive energy gained in the strong laser field, plus the ionization potential of the specific generation medium or the gas that you use. And so there's a lot of math and physics that go into this energy, but basically with 800 nanometer light at pulse intensities around 10 to the 15 watts per centimeter squared, we can produce XUV photon energies, between like 30 and 80 eV. And this is basically the focus of MEdge in transition metals. So this is pretty typical for a titanium sapphire chirped pulse amplifier output. And we have kind of developed the general setup that we use for this is starting to be mocked up in a lot of other labs as well. So the Baker group was at the forefront of developing this, and Dr. Baker in his postdoc just I don't know, like 6 or 7 years ago, worked on this initial setup, and now so we have it in our lab as well. But this is an ideal case for studying things like transition metal oxides or sort of dimetallic or multi-metallic complexes that have something within the 30 to 80 or 90 eV window. Okay. So I also mentioned that the choice between reflection or transmission or absorption sample models will be critical. So at the beginning of development, transmission model setups were the go-to. Many spectroscopic methods perform in this setup. So it's, pretty common to design, design an experiment that's based on this model. So basically you have your XUV light that goes through the sample and then, maybe interacts with the grating and then the detector. The limitation of transmission in XUV experiments is that, as I mentioned before, the XUV is highly attenuated in air and most materials. So your probe depth is going to be proportional to the attenuation coefficient, which is alpha, but your sample has to be extremely thin for this to work, for you to get essentially any XUV flux out of your sample. You also have to have a highly homogeneous structure, because if you start to probe through the bulk and things are changing as you go, your signal is going to have just magnifications of noise, and you'll have a challenge to discern what your data actually means. In addition to these problems, many theoretical studies have predicted that the equilibrium structure and the non-equilibrium dynamics actually of charge carriers are different at the surface of your material versus the bulk of the material. And this can be due to interfacial bonding. The surface atoms could host different coordination than the bulk atoms. And you also oftentimes see the segregation of structural defects. So defects oftentimes migrate to the surface of your sample, where they're maybe more stable. So all of these things have sort of motivated Dr. Baker to develop this reflection absorption mode. So this is actually XUV-RA spectroscopy, which is what's kind of coined in all of the Baker group papers so far. But we basically take our XUV light and reflect it off of the surface of the sample at a grazing angle. So we use 8 degrees. But here you can see the math behind what that does to the probe depth. Your probe depth is altered as a function of the sine of your incidence angle. And so here, for example, with a the theta being 8 degrees, the probe depth is reduced by a factor of about 7.2 or 7.3. So what we see is that we probe a much smaller region of the surface of our material. The line shapes of transmission versus reflection spectroscopy will turn out different in your final spectrum that you collect, but conveniently, this is relatively trivial to sort of compromise, because there are these developed mathematical relationships, the Kramers-Kronig equations, which allow you to basically extract the same resonance information from either setup. Slides. Okay, so now I'll just highlight one of our last benefits, which is specific to XUV-RA spectroscopy. So I mentioned before, but the surface sensitivity is going to allow us to really focus on the first few nanometers or atomic layers of the samples, which oftentimes is what we're most interested in. So catalysis would happen at the surface, a lot of magnetic properties sort of migrate to the surface, and so studying the surface or being able to study the interface between two different materials in XUV-RA methods is really another great benefit for us. So here we look at the XUV-RA intensity versus the X-ray photoemission spectrum quantification on this TiO2 silicon sample. And what we proposed in this paper was that the XUV edge intensity should saturate as a function of thickness as you get to the probe depth. So once you reach the full probe depth, you shouldn't be able to get any more signal. So if you're increasing the thickness of your sample, you wouldn't see the thickness going up once you get to the few nanometers that you are fully probing. And so this intensity saturation at higher film thicknesses correlates to fitting this XPS signal to an exponential. And so from quantifying this, we were able to determine that the probe depth in this specific case was about 3 nanometers. However, this is highly material dependent. So as I mentioned before, different materials can attenuate the XUV beam in different ways. So the attenuation coefficient allows us to quantify this probe depth directly. But you'll see that for most transition metal oxides that we've studied, this is on the scale of a few nanometers. So we're really just probing the top couple of atomic layers. And then finally, I'll just highlight, again, I mentioned before, femtosecond and attosecond time resolution. So in the Baker group specifically, we can map our instrument response function as a convolution of two Gaussians. We fit this from the bleach kinetics at the iron edge in hematite. And this can be anywhere from like 40 to 90 femtoseconds, depending on the fit and the material that we're using. But this retains the time resolution that's on par with these X-ray free electron facilities. But again, we're doing this in our own lab. So this is really benefiting us because we can monitor those ultra-fast processes with coherent light in the XUV window, just down the hallway. So again, to highlight our specific instrumentation, we have this high harmonic generation taking place in the gas cell. We have our sample in reflection mode, and both beams are interacting with that sample. Following that is our grating and our CCD, which we can collect really nice harmonics and translate that to really beautiful transient spectra. So lastly, I'd like to just highlight a few examples of some recent developments that sort of directly correlate with these benefits I've described for XUV techniques. So the first is being able to understand surface versus bulk dynamics in hematite. So hematite, which is this iron oxide complex, this is a highly earth-abundant photocatalyst. It's oftentimes used for model systems. Our group has studied it a lot, and many people have followed that up with more experiments, because this is a really promising photocatalyst, but it suffers from poor carrier mobility. So these excited charge carriers could perform photocatalytically, but instead they oftentimes self-trap, which leads to recombination and a quenching of any photocatalytic activity. And this happens on this time scale of a few hundred femtoseconds. So being able to probe where these electron and holes are moving within your system is really critical for understanding this process better. And what we find in our study was that there were predictions that indicated that the kinetics of polaron formation and hopping are unique to the surface versus the bulk, and they converge to bulk behavior within a few atomic layers. So here's a contour plot of the excited hematite state, excited with 400 nanometer light. And we see that, before time zero, there's no signal. And then as you excite your sample, you have this negative feature, which is there very early and shifts to, blue shifts to a higher energy. And then we have this positive feature, which grows in as well. So the model that was developed is that in the excited state, so we excite with our optical light, we have this initial charge transfer state. The excited electrons can couple to optical phonon modes in the hematite sample, and this results in an ultra-fast lattice distortion. And this is followed by polaron formation within several hundred femtoseconds. But if we take a look at the time scales, so specifically the polaron state, we can notice that in the bulk, which is the black line, this happens on a time scale of 90 femtoseconds. But at the surface with XUV-RA, which we can probe, we see that this is quite slower, about 3 times slower at 250 femtoseconds. So the next example that I wanted to highlight is the resolution between electron and holes in metal oxide, which I have described just briefly before, but in the molecular image of looking at a metal oxide structure, we notice that with a pump excitation from a valence to conduction band, we'll have a hole in our oxygen valence band and a new electron in our metallic conduction band. What this means is that a metallic M-edge transition, now we've lost some absorption potential because we filled an empty state here, whereas in the oxygen L-edge, we've now gained some XUV intensity because we have a new excitation pathway where our hole is. So by understanding this molecular picture, we can actually start to realize and predict what the XUV spectrum might look like. We would have positive intensity where we have new absorption pathways, and a negative intensity where an electron is now blocking an absorption pathway. So this translates to our spectra here on the right, where we have different metal edges, nickel oxide, a cobalt oxide, and iron oxide. Again, all of these will appear at different energies because of that element-specific core structure. But in each case, we have positive and negative features where we have new or removed absorption pathways. And in these 3 examples, we also see our oxygen L-edge. So we have a positive intensity here because we have that new hole in our oxygen L-edge transition, now in the 2p state. The only time we don't see our oxygen L-edge is in this iron disulfide, where of course we have no oxygen. But what we do see is that the iron positive and negative features line up perfectly with the iron oxide positive and negative features because that iron center is not changing. The oxygen L-edge, you'll notice, is shifting a little bit. This is a direct relation to how those oxygen 2p bonding states are covalently interacting with the metal center, and this can be shifted because of the covalency of that metal. And then at the bottom of this, we have this Zurch paper, which is going to directly show us a very similar trend where we have XUV differentiating carriers even in single element semiconductors. So this case is for germanium, where we have this band diagram which shows what we're exciting. Basically, a visible or near IR pump will excite electrons into the conduction band and leave behind a hole in the valence band, and the XUV beam can probe both that hole and that electron by showing us an increased intensity at the hole and a decreased intensity absorption where the electron is now occupying that state. So we have at the hole an increased intensity, and at the electron we have a negative intensity here. So these carrier dynamics in nanocrystalline germanium or other metallic systems can reveal separate dynamics that importantly decay together as those charges recombine. So that's really essential to assigning those carriers. Okay, and then the final example that I want to highlight is dynamics of spin states resolved by XUV spectroscopy. So here we studied some kind of complicated cobalt iron oxide. So we have two different metal centers, and this cobalt ferrite is a ferrimagnetic inverse spinel ferrite. So the iron 3+ centers occupy all of the tetrahedral and half of the octahedral sites, and then cobalt 2+ occupies half of the octahedral sites. So here we found that with XUV-RA spectroscopy, we were actually able to model and simulate the high spin versus the low spin excited states. And for the sake of time, I won't get into a lot of the details of that fitting, but basically we found that with this system, we could model that we have a high spin initial state where the cobalt is in the high spin, and then we have a low spin final state, which grows in as a function of time. So we're actually inducing a spin flip or a spin crossover event on the time scale of about 400 femtoseconds. So this is very similar to previous reports in Prussian blue analog systems. But we're able to resolve this ground state excitation into a high spin state and then decay into a low spin excited state. And this is really important because we're understanding charge carrier dynamics with spin sensitivity, which means we can model and sort of optimize materials that need this sort of spin control. Okay, so some future directions for the field that I'll highlight briefly. First, there's a lot of work happening right now to extend the capabilities of HHG-produced XUV light into the water window, which is between 280 to about 535 eV. This will allow us to access carbon, nitrogen, and oxygen K edges, which are really critical for most systems. We find a lot of carbon, nitrogen, and oxygen present in interesting metallic, catalytic, etc. systems. And we would also be able to study this in liquid environments, which is something we're limited to in the Baker group. We only can probe solid systems, and we could do gases right now, although solids are usually more interesting. So here's just a spectrum where you can see that the photon energy produced is greatly expanded. The second future direction I'll highlight is XUV magnetic circular dichroism, where we have the generation of circularly polarized coherent XUV light. So we produce circularly polarized rather than linearly polarized XUV light, and then we can use this light at the sample, which is in some magnetic field, to understand spin events at interfaces and at surfaces. So this is a figure from a different reference, which I'm highlighting here. They have a different setup. So the setups are not very uniform right now, but basically we are starting to look at XMCD signal rather than X-ray MCD or just traditional magnetic circular dichroism. We can extend this into the XUV window. And we're currently actively working on this very diligently. So hopefully we'll have some papers to show in the short term. And then the final application or future direction that I'll highlight is liquid sheet studies. So rather than liquid jet studies, which have been around for some time now, in the cylindrical jet options, we have strong absorption at the liquid edges of the jet. We have photon scattering happen and refraction due to that boundary between the liquid and the vacuum. And we also have mismatch between the jet diameter and the focus size of the XUV beam. So liquid jets have not really been a promising option for XUV studies, but by flattening those jets into the liquid sheets, which look something like this, we can actually have tunable, very thin sheets that are able to sort of propagate enough XUV light that we can study liquid samples, or we can study sort of a solute inside of some kind of liquid. Okay, and then the last thing that I'll highlight is just that there are some ongoing technological advances also underway to increase the brightness of some tabletop light sources. So the National Extreme Ultrafast Science Facility, or NeXUS, is one effort. So NeXUS is an NSF sponsored mid-scale user facility, so something between like a synchrotron and a lab-based instrument. This will be open access to users, but it is being hosted at Ohio State, and the director is Dr. Baker, my PI. So at the heart of this facility is a kilowatt class ultra-fast laser, which provides a 2 orders of magnitude increase in the XUV pulse repetition rate compared to traditional HHG sources like in my lab. And so we have these specs for our laser that's coming in, and we can drive attosecond and femtosecond XUV and soft X-ray generation with this laser. This XUV light will provide light for these experimental end stations. So we have X-ray absorption or X-ray reflection, spectroscopy, which is what I've highlighted today. But we'll also have XUV light for angle resolved photoelectron spectroscopy or ARPES, element-specific scanning tunneling microscopy or STM, and attosecond science with laser-induced electron diffraction or LIED. So this isn't the only facility. There's also one in Europe, which is the Extreme Light Infrastructure Attosecond Light Pulse Source, or ELI-ALPS. And facilities like these are really opening the door to a variety of nonlinear XUV measurements, as well as ultra-fast in situ measurements that are currently limited by just a lack of sufficient XUV photon flux at larger scale facilities. So again, just to highlight what Nexus specifically will do, I won't get into details here, but just a few examples of the different end stations as well as the time resolutions we expect here. So going down to the attosecond resolution, the XUV specs on target are, can be quite small and can have quite a broad excitation energy window. So 10 to 70 eV is traditionally what we do. That's what will be provided for ARPES. But for the XAS and XRS at Nexus, we'll have an expanded window from 15 up to 300 eV. So just to summarize with the Nexus facility, why are we focused on these higher repetition rates? What's this general benefit going to provide to us? Well, we're actually enabling a quantum leap in sample throughput. So in our current state-of-the-art high harmonic generation and a TI-SAF laser system, which we have in our lab with a 1 kilohertz repetition rate, Dr. Baker writes, okay, the required sample averaging is greater than 10 hours per sample. In reality, we usually average on a sample for a transient experiment up to a few weeks of experimentation. But at the Nexus facility, where we have 100 kilohertz, now suddenly this is going to take us, a 10-hour sample would take us less than 10 minutes. So this is going to really affect how much XUV science can be done by researchers across the country and really across the globe in general at this mid-scale facility. It's not going to be as big as a synchrotron or an X-ray free electron laser, but we're really going to enable a high throughput of different science and different projects that can come through. So lastly, I'll just put out our little advertisement that we have a user workshop coming up on July 25th and 26th. And because Andor is really critical to our development, we're using an Andor camera for the XAS end station. I'm not sure about, I work with XAS, so I'm not sure about the other end stations, but I'm sure Andor would be well represented at this user workshop, and you can hear about a lot more exciting and upcoming potential experiments that could happen at Nexus as its development comes to an end in the next year or two. So with that, I would like to wrap up my talk and open the door to any questions that you may have. Here I'm listing my contact information as well as Dr. Baker's if you have questions. And here is again the citation for the recent publication that I have sort of modeled much of this information on that goes into more detail there. And thank you for your time, and I'm happy to.
Thank you, Emily, for your informative presentation. We will now start the live Q&A portion of the webinar. If you have a question you'd like to ask, please do so now. Just click on the Ask a Question box located on the far left of your screen. We'll answer as many of your questions as we have time for. So let's get started. Our first question is, what kind of ionization medium is used for the high harmonic generation process?
Okay, this is a great question, and we actually had another question that came in on a similar topic. So in the Baker group, we typically stick with something like helium gas or argon gas. these provide us with pretty high flux in the region that we're interested in, which again is about 30 to 70 eV. But really any noble gas that has an ionization potential within the XUV window could be usable, and depending on the gas you choose, you can tune a little bit which energy region you get the most XUV flux within. And just to address the second half of the other question that came in about the spot size, so with our setup and our focal length from our toroidal mirror, we usually have the XUV beam that's about 1 millimeter in width, and then because it's at a grazing angle, it's actually stretched, so the height is usually like 0.1 millimeters.
Thank you. Next question. How thin does a transmission sample need to be to allow XUV flux through?
Okay, this is a good question as well. So yeah, one of the complications of doing a sample in transmission mode would be that the XUV is going to attenuate through the sample as it passes through the bulk of it. So the thickness is typically on the order of a few hundred nanometers, although you can, again, try to tune this depending on the material properties itself and the attenuation coefficient, as well as the total flux of XUV you have going into the sample.
Great, thank you. Next question. In example 1, why does the negative feature electron blue shift, but the positive feature hole not shift?
Okay, this is a good question, and this kind of highlights why we can really focus on differentiating between the electrons and holes throughout the system. So in the case of that example where we had excited hematite, the polaron formation was due to the stretching of the iron-oxygen bond, and as that bond shifts, or as that bond stretches, the shift is actually due to the electron becoming more localized on the oxygen itself from that metal to ligand charge transfer. So we see a shift in the electron feature, but not in the hole feature, which is unaffected in this lattice distortion.
Thank you. Next question. What is the timeline for the Nexus project to be completed?
Okay, this is a great question as well. So the initial NSF proposal was kind of frameworked on this 5-year plan, and we were hoping to spend a few years in design and purchasing and acquisition of everything, and then another couple years building and testing all of the systems. Because of the past few years, we've had a lot of shipping delays and manufacturing delays that have slowed this timeline down. But I think we are on track to have our first light this summer, and we'll begin building all of the beam lines and sort of finalizing the end stations themselves so that we can test and start to accept user proposals within hopefully the next 2 years. But I think this type of question will be answered in more detail at the user workshop if anyone's interested in joining in July.
Thank you. It looks like we have time for one more question. In a transmission experiment, how does the absorption through the bulk of the sample affect the collected data?
So in the transmission samples, as your XUV beam goes completely through the sample, you will have an effect of the absorption of the bulk of your sample. And because the bulk can have different properties and behaviors than the surface, your output data will have a lot of information on the bulk. And depending on what you classify as the surface, which in our group would be the first few nanometers, if you go through 100 nanometers of sample, you really can't say much about what you're detecting at the surface. You'll have too much interference from the bulk. And I think this is one of the biggest benefits of XUV reflection experimentation, where you can just isolate what's happening at the surface layer.
Great. And we do have time for one last question. Is the XUV technique suitable for nanoparticle samples?
Okay, that's a good question. So the main limitation on the XUV technique is that everything is happening under vacuum. So our group has started to dabble in some more complicated and sensitive samples. The vacuum conditions as well as the probe energy and intensity will have to kind of be investigated on an individual basis to determine the stability of the sample. But in general, nanoparticular samples are possible and have been studied in a few other XUV groups. So yes, it is possible, but a little bit more challenging.
Great. Thank you again, Emily, for your time today and your important research. We would also like to thank LabRoots and our sponsor, Andor, for underwriting today's educational webcast. Before we go, I'd like to thank the audience for joining us today and for their interesting questions. Questions we did not have time for today and those submitted during the on-demand period will be addressed by the speaker via the contact information you provided at the time of registration. Can be viewed and alert you via email for replay. Please share that email with your colleagues who may have missed today's live event. Until next time, goodbye.